much, Mathilde and the organizers, for putting together this very nice workshop. The landscape competes with the science. It's always nice. So I will discuss about the light statistics from big ensembles of quantum emitters, two-level atoms. And I will try to convince that even in the large n limit, we can have non-trivial statistics. Okay. So first, so I work in San Carlos. It's close to São Paulo because it's only 250 kilometers. It's close to Rio de Janeiro because it's only 600 kilometers. And the rest is a bit far in Brazil. For example, Felinto works Pernambuco here, which is already a bit far. But it's just 2 days by bus. Okay. So it's important to thank all the collaborators. So in San Carlos, we have both theorists and experimentalists, cold atom experimentalists. But the work I will present has been done in collaboration with the cold atom group in Nice, the trapped ion group of Lucas Rodic in Czech Republic, and Joachim van Zantier in Erlangen. And I will these different works connect. And so what I want to discuss first is phase randomization mechanism in light emission, which makes that we have thermal light around us most of the time. And then what happens if we remove this phase randomization mechanism? And so we try to deviate from thermal light. So it's really much into the lines of Arnaud's presentation and others to see what happens beyond Gaussian statistics and thermal light. So I will go very briefly here because it has been introduced in great details by Arnaud and others. Typically, we put light into 3 main categories. Anti-bunched light, when photons do not come together, and we call this photon anti-bunching. So here I will focus on this criterion, G2 of 0 smaller than 1, even if a more adopted criterion, more general, is this one. We have coherent light, G2 of 0 equal to 1, which means that the photon arrive at completely random times, so they can arrive at the same time or space. This is typically laser light. And photon bunching, which means that photons tend to arrive by bunch. So this sounds like, how to say, this could sound like a quantum effect, but we know there is a very classical interpretation, and actually, so classical light that we have around thermal light presents photon bunching, but this is a classical effect. And this has also been presented, but the typical way to detect a G2 of 0, and the point is it's a photon coincidence measurement. So you have your source you want to analyze, you divide it typically with a 50-50 mirror, and you detect, and then you do cross correlations to see if your photons arrive at the same time or not. The classical definition is correlation of intensity at time t and t plus tau. And in this case, the G2 of 0 is basically the variance of the intensity. But if you take this classical definition, of course, this quantity will always be greater than 1. So you have a quantum definition with what we call normal ordering, which connects to the photon detection theory developed by Glober, where you can have quantum light where G2 of 0 is smaller than 1. Okay. Fine. So now, going to my point, first thing, around us, we typically have thermal, sometimes called chaotic light. So from light sources, this is an old-style light source, from the stars. And typically, the hypothesis to show that you have thermal light, if you take, for example, the Ludenbach that was cited already, you need many emitters. So you have this in typically light bulbs or the stars. And you need the phase randomization mechanism. So because you want to say each emitter emits a given electric field with a phase which is random, and random compared to the other phases. It's not like each phase, all phases will change at the same time, but they change at different times and in an uncorrelated manner. And then you have what we call Gaussian variables. The electric field is a Gaussian variable. You have the Gaussian momentum theorem, and all moments of intensity are related. And you can have, of course, a quantum definition of this. So, first point is you can have classical mechanism to randomize your phases. And typically this can be temperature, which for stars, for example, will be very typical. So what happens? You send laser light, a given frequency. Different particles have different velocities, and so when you look in a given direction, you will get different frequencies. And this gives you a decoherence rate for the light, so a rate of coherence loss, which is related to the temperature of your sample, to the velocity. Okay? And I want to point out here that it's a completely classical mechanism in the sense that I can describe it with completely classical mechanism, which is the Doppler effect. Okay? You can also have quantum mechanism, for example, spontaneous emission. For a two-level atom, each atom emits a given spectrum with a given line width. And the important point is when you have many emitters, the different photons are completely independent. They will not interfere. This is spontaneous emission. Okay? And as discussed a lot in the 80s, this is a very quantum mechanism. So now if I go to two-level atoms with a given temperature, you will have these two competing mechanisms. So if I consider only elastic scattering, I will have only temperature. And if I look at spontaneous emission, I will get the two mechanisms. My atoms move, and in addition, I have spontaneous emission. So in this case, I have only my gamma thermal, and here gamma thermal plus the gamma of spontaneous emission. Now, if the thermal effect is much smaller than the spontaneous emission rate, I will have two very different rates between these two mechanisms. Okay? So a nice platform to investigate this are cold atoms, because the definition of cold atoms is that the Doppler effect is typically smaller than the spontaneous emission rate. And the control parameter we have in cold atom is the laser power, because if you drive weakly your cold atoms, you do elastic scattering. If you drive strongly, you get spontaneous emission. So an experiment realized in Nice, on the experiment led by Mathilde, was here a cold atom cloud. On very brown and twist setup with where light is sent on two avalanche photodetectors, and correlations between them are recorded. Okay? And then the saturation parameter is tuned to go from the elastic regime to the regime of spontaneous emission. And what we see is, if we look at the G2 of tau, two-time correlations, in the weak drive regime where you have elastic scattering, you have quite a long coherence time, which means a low decoherence time, and if you drive strongly, you have stronger decoherence. And if you compute it, you can check that this is associated to the thermal motion, while this is associated to the spontaneous emission. Which means that when you do this transition on the saturation parameter, you go from the classical mechanism to a quantum mechanism for the loss of coherence on the light. So these are for many emitters with some decoherence mechanism. And the question is, what will happen if I remove this decoherence mechanism? So I can try to go into a regime where I have negligible temperature, where it won't play a role any longer. And I can try to go to a fully elastic scattering regime, meaning I will lower down my saturation parameter to drive as weakly as possible my atoms. And it will be mainly elastic scattering. Then I will have negligible spontaneous emission and only elastic scattering. So in this limit, the intensity scattered is well described by linear optics classical optics theory. Basically, your cloud will behave like dielectric. You will have a refractive index. You can have speckle for disordered cloud or a Bragg scattering for an ordered cloud. But the point I want to discuss is, what are the photon statistics in this case? If I send coherent light on my cloud of cold atoms with a very low power, do I get coherent light out of it? And a very interesting point that was made already by Arnaud is that there is always spontaneous emission, and it's very important. And for example, if you take a single quantum emitter and you look at anti-bunching, which you will always have independently of your laser power, so even in the elastic limit, there is an interplay between elastic and spontaneously emitted light to produce the anti-bunching, okay? So on purpose, I don't use the word interference between elastic and inelastic or spontaneously emitted because it's not the same kind of light. I will use interplay. So this was first pointed out probably by Dalibard and Reynaud. More recently, it has been revisited by some theorists, Laucy and Del Valle, who did many works on this to show that, as Arnaud pointed out, if you start to select a certain spectral range of frequencies, you can change the light statistics. And two experiments were realized at the same time. I think Arnaud presented this one. There was a twin experiment, both on quantum dots. And basically, they changed the filter, and this changed the statistic. And if you have a very broadband filter, you take all the light, you have a very nice anti-bunching. And if you start to select only a narrow window of frequency, you go back to coherent light. And this was a very similar experiment on in another quantum dot group. Okay? Fine, so this is for single emitters, you need to frequency filter. Point I want to make is that if you have several emitters, you don't even need to frequency filter to get different light statistics. Because if you have several emitters, you already get interference from the elastic part. Okay? You have several emitters, you will have an interference pattern for the elastic part. Differently, the spontaneous emission from different atoms, which do not interact, will be isotropic. So you will have a pattern for elastic and some isotropic background from inelastic. Okay? One way to, okay. So it means that the balance between elastic and spontaneously emitted light will change with the direction of observation because your pattern of interference changes. So this was explored for two ions by Schmidt-Kaller and Van Zantier for two ions, and they could observe anti-bunching and superbunching. But the point I want to make is that you can do this with an arbitrarily large number of emitters. Okay? So for the theory part, I will move quickly on the emission, but we simply consider a product state of single atom steady state. It's a mixed state, so we take a product state. So it's a product state since we consider independent atoms. We don't even need interactions. It's mixed because we know we have to deal with spontaneous emission. It is important. We cannot consider pure state coherently where there is only coherence. And if we derive, then we can derive the G2 of 0, these two photon statistics. We get a bit complicated expression, but the key point is the following. We have an interplay. We can identify the interplay between spontaneously emitted intensity and elastic intensity, which I call coherent here. And this will have interference. This will be isotropic because my atoms are separated by several units of wavelengths. Okay? So I also have some 1/n corrections, which I always have in this kind of systems. And if I drive very strongly the system and I get only spontaneous emission, I will go back to G2 of 0, which is 2 times 1 minus over n, which is a typical correction you get with this phase randomization mechanism. Okay? Fine. So as I was saying, I have interference from the elastic pattern. I have something homogeneous for the spontaneous emission. Then if I look at what happens, what are the light statistics in the direction of a destructive interference, I can derive an expression for my G2 of 0 and show that it scales like 1 over ns, where n is the number of emitters and s the saturation parameter. So if s goes to 0, I can have very strong superbunching, arbitrarily large. For any n, I can have G2 of 0 as large as I want. And if I look at the condition for constructive interference, I will get Sn. So if S goes to 0, if I lower down the power, I can go for anti-bunching as close to 0 as I want, even for a large n. Okay. So one point is that if I have my intensity, so here I take a disordered cloud, I look at the intensity, I have some anti-correlation with the G2 of 0, okay? Because of what I said, destructive interference will go with a large G2 of 0, and constructive interference will go with a small G2 of 0. So now, if I look at my saturation parameter for a given number of atoms, if I drive very strongly, I go to G2 of 0 equal to 2. I will have this phase randomization mechanism. If I go for a very weak drive, I can have strong superbunching and anti-bunching, and in the same cloud. It will depend on the direction in which I observe. Okay, so of course the only problem is to go for very low power and still get enough signal to do your photon coincidence. So to investigate this effect, ion chains, such as the one in Olomouc in Czech Republic, are very nice because the atoms, the emitters, have a negligible Doppler, and you can really tune your configuration. It's really under control. So here is an example with 18 ions. So as usual, as any platform, the big limitation will go for a very low saturation parameter, because we don't want a low saturation parameter. We want that the number of atoms times the saturation parameter is quite low, okay? And this gives a very low coincidence rate for the photon correlations. But for 18 atoms, we already see quite clearly that the G2 of 0 in the destructive interference direction or in the constructive one are very different. Okay? So this shows that even in a larger system, we can see this modulation, this anti-correlation between intensity and G2 of 0. So if we go to smaller ion number n equal to 4, we can still see some anti-bunching and super-bunching, okay? So I want to point out that if we had n equal to 4 atoms and phase randomization, we would get a G2 of 0 of 1.5. But here we are able to go below 1, and here above 2. We also checked more systematically the anti-correlation between the intensity and the G2 of 0, and we're able to observe it. Yes. Again, I think here the saturation parameter is 0.6, so it's not very low, because it's a 3D scattering experiment, so light goes in all directions, so you need to put quite a power to collect enough photon in a given direction, but it was still possible to observe this anti-correlation. So, this. But theoretically, it's possible to go to as low anti-bunching or as large super-bunching as you want, as long as you're able to remove your Doppler effect, your positions, your fluctuations on the position, and any other decoherence mechanism. For example, with ions, the problem is that when you increase the system size, the number of emitters, typically the temperature rises. There are more fluctuations. And basically, when the emitters start moving, you start to lose your interference pattern. It fluctuates with time and you get something average and you will lose this effect. So you need some emitters that are really fixed to get this kind of effect and try to see strong anti-bunching and super-bunching. But in principle, it can be arbitrarily large, or so says the theorist. Okay, so the main point I wanted to make is that interference from elastically scattered light and the interplay with spontaneous emission, because we always have these two components, allows actually to modulate the light statistics. So in a single sample of quantum emitters, you can have the two kinds of light statistics, super-bunching, anti-bunching, provided you can remove temperatures or any other decoherence mechanism. And one point we want to investigate now is once you put interactions, what will happen? Because typically you expect broadening, you expect collective modes, and in the end, if I take a piece of glass, I know I will not get anti-bunching or super-bunching. I will send coherent light, I will get coherent light, even if there is because there will be some coupling between the emitters anyway. So there should be a transition where my decoherence interactions probably kick in and destroy the effect of strong super-bunching and anti-bunching. So that's it. Thank you very much for the attention.